Hello and welcome back to a new video here on the Lötwig Fusel channel. Now in today's video in real-time rendering we're gonna talk about project and resources. So in the last video we talked about geometry and how we can kind of like define a pipeline, a way to import this geometry into our application. And what we're gonna do today is we're gonna take right into how we're gonna define them in terms of projects. So the idea is that we are not like crafting our geometry out of thin air or using some predefined code that is hard-coded. No, the idea is that it's all configurable and flexible so that we can define multiple workflows that we need in real-time rendering. It's important. And what we want to do also is we also want to expand this so that we can not only use this for geometry, but also later for animations, maybe like even special geometry that needs to be imported, like point clouds that are used to spawn like foliage or something like that, and just have a bit of a more flexible system, right? Also for textures, shaders, and all of the fancy rendering stuff that's going to come in the future. So that's what we're going to talk about today, how we're going to transform that into a project system, and how we're going to define resources in that. Alright, so welcome back, real-time rendering. Now, let's get directly started and talk about projects and resources. Now, we're going to start by taking a look at why we actually need a project system, right? Couldn't we just put all the resources in one directory? Do we really need a project system? That's one question that we need to do. Then we're going to do a recap on the geometry workflow in RTR, so what we have talked about in the last video, and we're going to recap this, find out what was important there, and then we're going to synthesize out of that a way how to uniformly define resources. So we're gonna kind of like find a way on how to do this in general for resources that also fits our geometry workflow that we have already talked about. And after that, we can talk about the actual format on disk, because that's important, right? How do you want to like represent that format in on the disk? And then we're gonna go and take a look at an example, not only in VS Code. This is outdated. We're also gonna take a look on Visual Studio, because I've already implemented that. I think it's better if I have already implemented that so that you can see how it goes, because implementation of JSON is not that interesting, right? Okay, so let's get started. Why do we need a project system? Well, in general, we could get away with just defining everything with single files, loading all these files step by step in there, but that's not the point, right? We want to organize our rendering. We want to be able to define like multiple scenes, multiple like tech demos that we can then work on to get the best out of them, right? So the idea is we're going to write tech demos with our rendering framework that you can also run on your system, that can be exported to something that you can showcase to your friends and kind of like have a player and a project file, so that you can actually like show this around, test this in multiple hardware on multiple GPUs, and just have a kind of like mini game engine that really isn't a game engine because it just renders. That's the point. And if we're doing that, we want to organize everything into projects so that you can easily open up a project, edit it in the editor, tinker around with the shaders, save it, load another project for references, and have like the general systems that you want to have if you do work with like a game engine, right? Like a game engine. You have a project, you open up, you work with them. So yeah, in general, we want to define how resources are loaded from where, define additional properties for resources, define how resources are used. This is just a few more feature-less explanations about why we need it. But the general idea is, right, we want to have a project system to kind of like have a project, like in Visual Studio. We always have one. It's also not that complicated to write a project system, especially with modern libraries and modern file formats. And it's just like required to write like 2 functions per struct. All right, so let's now talk about how the geometry workflow in real-time rendering is, so what we have done last video, because we want to use what we know to build a system, right? Because we're not going to write a project system or a resource system out of nowhere, right? If we want to write a project system, we kind of like need a definition of how a resource looks like. If we know how a resource looks like, we know how we can integrate them in the project system. But to know how a resource should look like, we actually need to take a look at the existing use case for a resource. resource. And that existing use case that we already have is geometry. Because geometry is kind of like our format. This is what's defined now. We in general know how geometry works. We talked about this in the last video. We haven't talked about that too much, how this is represented, but this is like the topic of next video. In this video, we in general just take a look at on the abstract view of how our geometry workflow worked, and then we're going to synthesize out of that a concept for a project system, or first for resources and then a project system. All right, so what was our workflow? Let me maybe go through that very quickly, right? So the idea is we have a 3D modeling tool that exports ourselves an FBX or OBJ. When we are working with our editor, we want to live import this into our application and create an optimized binary intermediate out of that that can then be used to be sent to the GPU and rendered. Now, if that OBJ file changes, we want to reinvoke this if we are in our editor so that it gets converted again, uploaded to GPU again, so that we always have an up-to-date version of our image. Now, when we are later going into shipping, which is something that's still way behind, but we want to go to that at some point. And at this point, it's basically that we have like a tooling application that takes the FBX and creates also this optimized binary, which then can be used and shipped with the application. We also, of course, provide maybe a few metadata to this rendering tooling application so that it can run properly. Now, what could also happen is that we have some live metadata that is basically generated by the real-time rendering system. For example, at some point, we might integrate physics just to use the physics in rendering, right? To have objects moving around, falling, colliding, and maybe even a bit of wind simulation so that we can maybe do a bit of fur, hair, or grass, or foliage in general, so that we have kind of like some live-changing metadata that's then like live computed into some optimized binary rendered on the GPU, which might be completely like pipelined to the streamlined to the GPU, but that's a general idea, right? You can also have some live metadata or some static metadata also producing optimized binary intermediates. Now we abstracted this away into a concept of generators. So we kind of like have the data in the input format A, which then basically flows through a generator and produces an output format B, which could again kind of like be seen as a input format C that's then used by the generator for the output format D. So the general idea is we have a generator here that takes some configuration and some input and produces output, and these generators can be chained for resources. So for example, importing a 3D model. First of all, the 3D model needs to be imported, and then it needs to be uploaded to the GPU. So there are kind of like two steps required, and these two steps could be kind of like seen as a generator for generating the resource how we need it and how we like it. So that was kind of like the idea here. Now, how do we use it? How we going to transform this into a general way of doing resources? Well, we just use the same like we have done previously. Now, in general, every resource is going to have generators, so we're always going to use generators. So, for example, also if you want to just generate like an image that just has one color, right? You could provide the color, use a generator to output an image from that color, or you could call a generator to process an input file, which might be a PNG file, to a format that the GPU can understand. So the general idea is that we're going to use generators for everything. Now, of course, we also need to identify resources, and identifying resources could be done by names, but I don't personally like the idea of naming resources that much. There are modern ways. In this case, we're going to use a way of defining GUIDs, so global unique identifiers, that can be kind of like generated on the fly, and each resource is going to be represented by one GUIDs. Resources are going to use URLs. URLs are not going to be like the URLs that you use on the web. URL in general just stands for Uniform Resource Locator. It's used in the web for defining web pages, but we're going to use the URLs for grouping and organizing our resources into a hierarchical structure that we then can display very easily. Now, what I also want to use is a HTTP like MIME type. So on HTTP, the network protocol for the web, what's used for displaying your web pages, they are using MIME types to define what was being transferred from the web server to you. There could be like defined that the data is JSON, or that it is HTML content to be rendered, or a file to be downloaded. This is all done via MIME types. the web browser kind of like detects on what MIME type was sent to it, and then it decides what to do. If it shall render it, provide it as a download, or format this and show you nicely the output of the JSON that was sent. So in general, it's just like an identifier what type it is, or as I have written here, a classification of what the resource is. Want to use something here as well. This is then going to be used to show you the proper controls on the UI side. So inside the editor, it's going to take a look at the MIME type, and then it's going to bring up the correct UI for showing you the properties of a resource. Now, I also, of course, want to have a property storage in a resource, because you might want to change things around, right? If you have an image that shall be rendered on the GPU, you might want to control if it should be scaled down or not, maybe, for example. But that's something that we're going to talk about later, like MIP mapping. This is something that could be defined on a per resource type if this is MIP mapped. And we're going to get to what MIP mapping is. Now, what we also want to have is hot reloading. This is something that you should not be too concerned about. This is something that I'm mainly concerned about. You just need to be concerned about the generators. I'm going to implement with you the generators, but all the hot reloading features that generators are invoked if a resource is changed. This is all something that I'm going to implement under the hood. The actual implementation, what's happening, doesn't change because we're going to use generators, but when the generators are invoked, this is something you're going to leave up to me. There is going to be a strict way. If you start the application, all resources are loaded, and then if a resource changed based on a hot reload trigger, so we're going to set up triggers that are going to listen for events that happen, for example, a file that changes or a resource that is modified, then I am going to write a system that automatically re-invokes the generators. You don't need to be concerned about that. It's going to be a very handy feature. That's a feature that, especially when we get complicated, really is a 100% required. Because if it would not be there, the system, we would have issues. Because then we would need to restart the whole application every time we do a change, right? And then, for example, if we are later on getting into more complicated setups where we do lighting and have multiple light sources, maybe multiple objects, and we move these lights around and have an edge case where something looks bad, we change the shader, we need to restart the application and need to restore that whole state. So the idea is that we keep moving the lights, everything stays as it is. We can modify the shader, the actual code that's responsible for rendering. And it's automatically going to change without restarting the application on the fly without you even noticing. That's the idea, at least. So that's also something that we want to have here. You should not be too concerned about that because the implementation it's actually straightforward, but I do not want to go into that because it mainly is how systems work in the background and not what you should be concerned about real-time rendering. Now, the next thing that we need to actually talk about is the actual format on disk. Now, I have some very distinctive, things that our format on disk needs to fulfill. I want to have a format that's human readable because we're going to use version control with Git, right? So it should not be a binary format. You should directly see what the changes are. You should be relatable to these changes, right? If you see that the line has changed in a project, you should definitely be able to tell what has changed. Okay, MIP mapping from off to on, for example. Directly see this, MIP mapping, double point on or double point off. So have a direct format that's there. Then I also want to have a structured and hierarchical layout because I want to have generators, multiple generators. Generators are defined by like names, properties, maybe triggers, configurations. So I want to have a nice and hierarchically structured view of these configurations so that we can easily see them in a hierarchical order, but at the same point be simple and not as convoluted as, for example, XML is. So this is why I have chosen JSON. JSON is a JavaScript object notation. It's not really something that has been invented for C++. However, there are very efficient and easy to use implementations also available for C++, of course, especially like in Loma JSON, what we are going to use in this project. And it's a good thing. And I personally am a big fan of JSON, and this is why we're going to use it here in this project. All right, before I wish you fun, let's actually talk about implementation, right? Because we have been theoretically quite some time. Right, so now I have Visual Studio Code up and running, and I have the code here for real-time rendering. This has actually changed since I have done this small video where I've explained how we're going to do modular software. We are not going to do modular software because the way that the project management and dependency management was set up on the other project that I had, it was a bit convoluted and build times were extremely high because of some, I would say, poorly written Nugget packages, but I do not want to blame any big company for how they do their stuff, right? They do their stuff for different use cases than I do, and not writing 5 modular systems that work. It was just a bit of a mess on how was a bit tedious to use. So this is why we are on the new system here. You shouldn't really mind because it was not an official video in RTR, so that's good. Now, we today will only want to consider the app folder here while we are in Visual Studio Code. The app folder has a subdirectory projects. Just for explanation, the app folder is the folder that's used for debugging. So this is like the debugging directory where we start, the working directory for application and debug mode. And you can see that we have a subdirectory projects. And in this subdirectory projects, we're going to have multiple projects here. Currently, I just have one, which is called example. And you can already see that we have a few files in here. Don't mind these Git files. These are just for properly integrating projects with Git. The main file that we're going to have here is the project.json. The project.json is defining the general layout of a project. Maybe let's make this a bit bigger because we can. And as you can see, it's really simple, right? We have a copyright, a name of the project, we have a version, and we have a list of resources, an array of resources. Now, there's already something that you can see here. This looks a bit odd. Yes, this looks odd because this is a UUID. UUID means, or it's actually a GUID, Global Unique Identifier, or UUD, Universal Unique Identifier. The general distinction between UUIDs and GUIDs is that UUIDs are only like unique locally per application per run, so you could actually use an integer for UUID. So you could also use the distinction between UUIDs and GUIDs is always depending on how you look at things. But in general, they are kind of like the same, but not. GUIDs are a bit more globally unique than UUIDs, while UUIDs sometimes are just referred to something, all right? UUIDs just need to be unique per application, per system, per startup, while GUIDs are kind of like seen as global unique identifiers, and globally basically just means we issue a GUID once, and then it's globally until infinity. But that's also what is depending on how you ask people. All right, so this resource GUID is actually referring to that resource directory. In the resource directory, we have a subdirectory which has the same name than this resource ID. And this is in general how we roll. We're going to have a subdirectory per resource so that we can also have access and store files dependent on that resource. For example, maybe shaders might be stored here, or a pipeline state might be manually serialized into there, just so that we are a bit more flexible and have a bit more options. Now, every resource is going to have a resource.json. The resource.json file is in generally going to define the definitions for that resource. This is a bit more complicated, so let me actually collapse everything in here. Now, the basic setup here is a type and the URL. The type is in this case mesh triangular, which means this is a triangular mesh, a mesh that is built up out of triangles. Now you can see that we also have this URL, which is the uniform resource locator. In this case, you can see that it is stored as mesh example 3D mesh. This means that it goes into a subdirectory mesh, and its name is example 3D mesh. It's just a naming that is independent of the actual resource, which also means that you can name and move stuff around without links breaking. Now you can see that we have 3 more options here. First of all, we have properties. Properties are used to just have a very, very basic way to just throw in some key value data without any further hassle. So just a bit of storage in here. There's just some dummy value in here currently. Now, hot reload shouldn't be too big concern for you, but in general, these are triggers on when the generator should be reapplied. In this case, they should be reapplied if that resource changes, which is the current one. This is probably a feature that I'm going to remove and do as a like automatic thing. If the resource changes, it's always going to regenerate it. This shouldn't be something that should be explicitly noticed. However, this is still all not working and still all in like a concepting phase. This is why I've put all these things in here so that it's a bit more clear. As you can see, we also have a trigger on the file. This is just specifying a file name, and if this file changes, it should also be hot reloaded. In this case, it's an OBJ file in the data directory, which is kind of like the file that's represented by, or the file, if that file is represented by that resource. So if that file changes, for example, if you re-export this from your digital content creation tool, then this should also hot reload automatically. That's the general idea. Would this be required to hot reload OBJs? It would probably not be that required. However, since we're going to have this all uniformly defined with generators and shaders that going to trigger that, so it isn't like more work to, in this case, the only work that's really required to have that feature additionally in is just write that string here. That's how it is planned at the end, that the hot reloading and stuff is all done automatically. Now, what we are really interested in are these generators. These generators define how this resource is generated. Now, you can see that the generator is actually containing, in this case, 3 entries in this array. And these 3 entries are processed in order. So they are not random in here. They are actually ordered. And I think they should also be ordered. It's probably, yeah, it is ordered. If it's not ordered, I need to reconsider if I'm using the right JSON library. But yeah, I think that maybe arrays are always ordered. I'm not quite sure of that. Now, the general idea is that the generator has a configuration. So, for example, this generator, that first generator, is invoked in the editor and baking, which in general means if we are baking means taking our development resources and transforming them into a resource that can be deployed to like a customer, a player, a user, whatever. This is called baking. And editor is kind of like the workflow called when you're actually working with the project, right? You're opening up the editor, you're opening up the project. So something needs to be done with the raw resources to be available for use in the editor. Now, in this case, you can see editor and baking are using the same tool, and the tool is called, or not the same tool, the same generator, and the generator is called import triangular mesh. What import triangular mesh shall do, it shall take that OBJ file that was created by, for example, Blender, because it's a Blender monkey, right, Suzanne, and it then shall bring this into a binary format that can be read by the GPU. That's the whole purpose of that generator here. And to use it, we of course need to give it a few properties. We need to tell it which object it shall load. In this case, it's Suzanne.obj. And since for especially FBX files can have multiple objects in one file, we also need to kind of like define which sub-resource of the file we are using. In this case, we are using a mesh. A OBJ or an FBX could also contain textures, animations, bones. I already had animations, bones, and like special properties, lights, and stuff like that. So it's kind of like important to tell it what to load. In this case, it's a mesh, and it's the first mesh that's in that file. In this case, there should be only one mesh in here, and this should be the only thing in that OBJ, but still we need to be aware of that to be able to load that. But that's something that we're going to talk about more into depth into the next video, where we're actually going to implement this import triangular mesh generator. All right, now the next generator here is only going to be applied at runtime, right? So these 2 generators were done in the editor and baking, and this generator runs at runtime. Now, what this generator does, it's going to load a triangular mesh. So as soon as we are at the runtime, which means we are using the pre-computed binary data, and we are consuming it at runtime to present to a client, customer, player, whatever you want to call the one that is using the final output after your development. And in this case, it's going to load a triangular mesh. So on editor and baking, we are importing it, and importing means taking the OBJ file, generated that optimized binary. So on baking, we are generating that, it's going to be stored and shipped. On the editor, we are generating it, storing it into memory. Now, as soon as we are at runtime, this pre-generated one, which was pre-generated by that step here in baking, by the first generator, is then loaded. So on runtime, we load the pre-generated one into memory. So this is kind of like the flow. We are baking it into an optimized version, and at runtime we load this. On the editor, we don't need loading because it's already persistent in memory, and it's going to flow down the chain. And actually, how does it flow down the chain? Well, with the last generator, which runs at editor and runtime. So not during baking, because this one is actually consuming the resource and uploading it to the GPU. So this can be only done at editor and runtime, and it's also done at both, but because at the end, everything needs to be on the GPU. So editor, runtime, name of the generator, upload triangular mesh. With these properties, these are also still placeholders that are probably going to go. And the idea here is to upload the triangular mesh. So if we recap that, when we are baking, we are just invoking the first generator, which is importing the mesh and storing it somewhere. When we are on the editor, it is imported from that OBJ file. That generator is skipped, that's only for runtime. And then this generator is invoked, which uploads the triangular mesh to the GPU. So our editor workflow is imported from the OBJ, uploaded to the GPU. While when we are at a runtime, so at a distributed build, that one is skipped because it's only on editor and baking. No, I want to collapse that one, but that one is used at runtime, so it's going to be loaded, and then that one is going to fire in, and it's going to be uploaded. So on the editor, we have a workflow of importing, uploading, on like on a deployment build, on a shipping build, we are having the configuration of loading and uploading. So import, upload, load, upload. And that's the idea here, so that you can define different workflows here that are dependent on what you do, right? So this is just a very in-depth explanation how these like file formats work. Now let's actually take a look on how we can use them. Well, we can use them like that in our C++ application. Now the first thing that I do is I'm going to initialize my log manager. The log manager is just there to do logging outputs. Very simple, not really much behind that. Then I'm creating a project context. The project context is going to be a context where I can actually load my project folder in here, which you can see that I do here. So I'm going to do this here by calling the open function, taking the current path, going to the projects directory and the example directory. This shall then open up the project and load it in. Then I'm just going to do a quick output here. I'm going to output the project name to the logging system, and after that down here I'm going to save the project if I have done any changes, and then I'm going to close the project and return 0. So that's just a very simple flow, and if everything works we would expect the name of the project to be printed, which we want to do here of course, which should be example project. Alright, so let's go and try this out, what we got. So let's run this and see. Recompiling that, and then it's gonna of course move this to a different directory, and now you can actually see here it is working. Oh no, don't want to put this too much off. It's gonna give us a few more logging outputs from the pieces. The pieces is the project system, opening project example, project name example project, saving project, closing project. So you can actually see everything works. Now to show you how these data structures are loaded out, let's actually take a look at this here. We actually have a pproject.h. pproject, it's just a simple struct with a name, version, and copyright, plus an unordered map of UUIDs to a RV proxy of resources. RV proxy is just handling how you access the resource and if it needs to be saved. But yeah, that's not really something that you should currently be too concerned about. Yeah, it's just handling that saving is done if it is required, so that we are not always saving resources. Now, resources are also very simple. They have a GUID, a type, a URL, as the vector of hot reload triggers, an unordered map of properties, and a vector of generators. The generators itself also very simply defined. They have a name, a list of configuration, and of course some properties. All of them have a bit of serialize and deserialize functions that are doing serialization work, but that's not something that you should be concerned about. The same with the implementation. It is just some way around navigating JSON and extracting it and properly iterating it. So really just a bit of work, but not really much to do. Now what we could do here just to be fast is just do a simple output again. So I'm going to again get the logger here, maybe do some debug output and just say something like generator, and then maybe print out all generators that we have on our first resources. So let's do auto resource, or let's do auto reference resource equals ctx get, which gets our project. Let's go to my resources and let's say begin to get the first one and dereference it. Now this is now this RV proxy, so we should have the way. Oh no, it's off because we need the second one. Dereference, or we can just say maybe something like second, like this. And now you can see like we have this R and V for read and write is dirty, clear dirty flag, and a few functions here. So what I could do is I could do a quick call to read to just get read access to it, which should now actually be a const reference then. What I can then quickly do is say for auto reference generator in resource generators, and I could do something like generator and then maybe input the name of the generator, so generator.name, just a very simple logging output. And now I should also get the name of the first resource that we have in here. We just have one resource. This is why I have done this with like begin. And we should get the 3 generators: import triangular mesh, load triangular mesh, upload triangular mesh. So it's really quite simple in how it all works. Now there's of course a bit more on this project currently. I'm also having a bit of infrastructure for logging and tasks in here. Because Directly Serve is by its nature async, we want to actually imply a complete async concept to that, or as much async concepts as possible, especially when it comes like for file importing and offloading work. So we do want to have a streamlined kind of like single threaded approach. However, all tasks that can be parallelized will be parallelized and will be done with tasks. So we're going to have a nice and simple streamlined process, but it's going to be divided into tasks that might even dispatch subtasks, like especially for loading. Right, loading can be speeded up very simply. And it's also nicely abstracted, so you don't really need to care about how tasks work. All right, so this I think gave a good overview on how my resource system works, and yeah, I hope you enjoyed. Yeah, it was a bit more complicated and maybe a bit into detail today, and still not really on the point where we are going to get to real-time rendering. But on the next video, we want to actually talk about. Next video is going to be a half theoretical video and a half practical video where we're actually going to go into and start implementing the first generator. I think we're gonna at 100% already do the import triangular mesh, maybe even the load triangular mesh, but probably just the import triangular mesh. The other ones, that one I'm probably going to just implement on my own, and that one is going to come later on when we are on the context of the actual GPU. So yeah, thank you for watching. If you enjoyed, I would really like it that you comment on the video, subscribe to the channel, and like it, the video. It really helps. So thank you for watching. Make sure to like and subscribe, and have a nice day. Bye.